recording. Okay. So last time we talked about improper integrals, right? So in particular, we still assumed that you had a bounded function. We said if you wanted to integrate, from a point to infinity, like on the interval 0 to infinity, how would you do that? If you wanted to integrate from negative infinity to 0, how would you do that? And then we also talked about how you'd integrate from negative infinity to infinity. Now, fairly typical mistake that some students make when you're integrating from negative infinity to infinity, and maybe you'll need to look that up, so if you take a second, it should be the last thing we did. But the definition, right, of the integral from negative infinity to infinity is you pick some point, any real number. You check if the integral exists to its left. You check if the integral exists to its right. If both of those integrals exist, then you say that the integral from negative infinity to infinity exists, and the value is its sum, right? So what's very tempting, though, is to just kind of do it in one shot, right? So we should say, uh-oh. So it is tempting to, okay, hold on. Yeah, so apparently, despite having a fire test yesterday, we're going to have one today. So I'm going to mute myself as occasion rises so that you don't have to listen to the screaming of it. Anyway, it's tempting to compute this as follows. Yeah, it's just, I don't even understand. It usually happens on Mondays, and it for sure happened yesterday, but I think like this week is the big one where they're really doing all of the fire things like in great detail. Okay, so it's tempting to try and do the two-sided integral like this, right? To take the integral from negative x to x or something else, right? If you want to do like negative x to 2x or anything, and to see if it converges by doing this sort of integral. But this does not work. Okay, and the reason it doesn't work is because we can take a function that for sure will not converge and get a finite value if we do this computation. Right, so for example, so we have students do this all the time, and like I said, be careful. So what if I asked you to compute the limit as x goes to infinity, negative x sine t dt, right? So this thing is, it's an odd function, and I'm integrating over symmetric integral. And so when I integrate from negative x to x, this limit or the integral is just 0, right? So when I take a limit, I definitely always get 0 as well. As x goes to infinity. And that's 0. So if we trusted this, we would be tempted to say like, yeah, maybe this integral actually exists. But we actually would run into an issue if we did something a little bit different, right? Like in theory, it shouldn't matter if I went from negative x to x. What if I'd done negative x to 2x? Right? Like if I'd somehow integrated the right-hand side twice as fast as the left-hand side, that really shouldn't make a difference, right? If this integral converges, it shouldn't matter that I did the right-hand side twice as fast. But in the case of sine, if you did the integral from negative x to 2x, you actually would get it does not exist. And so suddenly this improper integral, if we were to try and do it this way, suddenly it depends on how quickly we integrate each side, right? And we feel like that shouldn't matter. Right? At the end of the day, if it exists, it doesn't matter whether you do all the right-hand side first, then all the left-hand side, or did them at different speeds, you should get the same answer. So we have to be careful with this, right? This doesn't work. Now, this doesn't work for showing convergence. That being said, if you do know somehow, if you do know that it converges, this will give you the right answer, right? So note, if you know that this thing exists or converges, let's say, then you can do this two-sided limit thing, right? So you can't use this to prove that this converges, but if you want to use it to figure out what the value of the improper integral is, then you can do that, right? It's just that sort of situation is kind of weird because how would that happen, right? Usually the way that you show convergence, and especially if it's something that you actually can compute, because today we're going to prove a bunch of convergences without actually computing them. But if you're interested in the value and, like, how did you know that it converged ahead of time? Like, you should have just done the two one-sided improper integrals and added them up in the first place. Like, this seems like unnecessarily an extra bit of work. So just generally avoid it. Here's kind of something you can keep in mind, but it's not, it generally is not useful in practice. Okay. Okay, so that takes care of that. So now we're going to dedicate pretty much the rest of today to just proving a bunch of convergence tests, like how do we tell whether an integral converges or diverges? And like, we're going to have no idea what the value is, right? Our only goal is to test whether these things are going to converge or diverge. So without further ado, I'm going to introduce two lemmas here, and we've actually already proven these lemmas. You actually proved these lemmas. So lemma number one. So suppose A is some real number, and I give you two functions. Okay, so I'm just going to do integrals from A to infinity, but of course all the results hold. Sine doesn't work because it's odd, right? And it definitely doesn't converge. So if you try and compute one of the one-sided limits, right? Like try and compute B goes to infinity, 0 to B, sine t dt. B goes to infinity. So what's sine negative cosine? Right? And that gives you the limit as B goes to infinity of, so minus -1. So again, so 1 minus cosine B. And that does not exist, right? Because cosine just keeps oscillating. And so as you write it, cosine doesn't have a horizontal asymptote. So when you take the limit of cosine as B goes to infinity, you get something which doesn't exist. So this tells you that the one-sided improper integrals for sine don't exist. And because the one-sided improper integrals for sine don't exist, its two-sided one can't exist either. Does that make sense? So even though this evaluation gave us a finite number, it lied to us because that number, like this improper integral does not actually exist, right? This diverges. And yet doing this two-sided thing gave us a finite number, right? So that's why we're saying like we have to be careful with it. Okay, so like I said, I'm only going to do the integrals from like something to infinity. It's up to you to restate these things for negative infinity to some number or negative infinity to infinity. All the results hold, but they have to be restated. So this is true. Suppose A is a real number and f and g mapped are such that f of x is less than or equal to g of x for all x, right? Okay, so the result I want here then is if the limit as x goes to infinity, f of x equals infinity, okay? So here's our lemma. Basically, you've got these two functions, and you're looking at what happens as they go off to infinity. F is always less than g. If f has to shoot up and go off to infinity, well, g can't possibly have a horizontal asymptote, right? It's bounded beneath by f, and f is itself going off to infinity. So this forces g up to infinity as well. You prove this. This was test 2, question 1.1. Okay, so you all did this yourselves. And if you don't feel like you did it correctly, the solutions are online, right? Wouldn't hurt, just try it again. It's not too bad. Okay, now there's a second one that we need. How did this one go? So if f, again, maps a infinity. I'm not going to now say, you know, a is a real number. I don't want to just include that every single time. It's just an arbitrary real number. So if f maps a to infinity is increasing, do I want increasing or can I use non-decreasing? Yeah, non-decreasing is fine. And bounded from above. Then it has a horizontal asymptote. Okay, and this was test 2, question 1.2. I might have stated it a little bit differently, but that should be morally it. Like so. Okay. Do you guys remember that? Hopefully I stated those more or less correctly. The second thing in particular, I really do recommend that you reprove the second lemma, even if you don't worry about the first lemma, whatever. The second lemma, though, is definitely worth redoing. When we get into sequences and series, this lemma is going to reappear. We're going to talk about a sequence. We're going to say if a sequence is non-decreasing and bounded from above, then it has a limit in exactly the same sense. And the proof is identical. This theorem is so important in sequences that it has a name. It's called the monotone convergence theorem. Okay, so it is worth reproving this. The proof is, again, it's almost identical. Yeah, so it's worth proving if you have it. And yeah, this is almost exactly how these things were stated, except I use capital F's and capital G's here instead of lowercase f's and lowercase g's. Okay, so, but you've already proved all these, right? You did that in test 2. Okay. Oh, you know what? I actually wanted to do a different test first. Whatever, I can still prove this. Oh, maybe, you know what? Let me introduce this as a lemma as well then. Lemma. Is the second lemma true if the domain is only the rationals? Because I remember using completeness axiom. Yes, it should be, right? Because the issue is, so you can still use the completeness axiom. It's just that the limit might be a real number, if that is satisfying enough for you, right? Because you can, I mean, are you saying, is the codomain also have to be the rationals or just the domain? Yeah, but just the rationals in the domain or the codomain. Okay, yeah. So then the theorem is not true because, right, we do need to use the completeness axiom, but the problem is that, so the limit of this function is going to be the supremum of f, right? And of course, the problem, if the domain is the rationals as well, is that the sup could be a real number, right? Like it's relatively easy for us to construct a function from the rationals to the rationals, which is non-decreasing, bounded from above. And if it had a limit, its limit would be a real number, right? So as long as we were allowed to do that, right, and allowed to say the limit exists, but it could be a real number instead of just a rational, then this lemma would be true, but it wouldn't be true otherwise, because restricting to the rationals isn't prohibitive. You know you have a completeness axiom if you think of the rationals as sitting inside of the reals, but of course your point is precisely that there is no reference to the reals, right? So as long as you say the limit could exist because it could be equal to a real number, the lemma is true. If you demand it to be equal to a rational number, this lemma is no longer true. Right? And just go through it, like try to do the proof and see what happens. But yeah, we could totally just make it, you know, approach the square root of 2. Like that wouldn't be too bad. It wouldn't be too hard to do. Okay, so the final lemma we're going to have here is called the p-test, right? Which sounds like something your employer will make you do to check if you've been taking drugs. And it goes like this. So I'm just going to I'm going to be a little bit lazy when I write this. 1 over x to the p dx converges if and only if p is greater than 1. Okay? And this is another one of those things, like some people talk about substitution and call it U substitution, and I think that's stupid. But this one's fairly universally called the p-test because they let that power be p. P for power, I guess. This proof is trivial. I don't want to, well, maybe it's not trivial, but it's very straightforward, right? And it's just you do exactly what you think you should do. So if we do 1 over x to the p, it's really just a computation sort of thing. 1 to, no, b, 1 over x to the p dx, right? We know how to integrate that. It's the power rule. I guess unless p is equal to 1. So let's kind of assume right now, I guess this is case 1, p does not equal 1. Let me move that. All right, okay, now we can do it. No, not to screw up your notes. I'm sorry, just not to screw up your notes. Everything I had written there doesn't actually need a case yet. Let me put that back up here. And now let me write the cases down. Okay, so case, just in case you're taking notes with me, I don't want to screw up your notes. Of course, the potential is now that I've really screwed up your notes. But anyway, whatever. Case b does not equal 1. So this is going to be the limit as b goes to infinity of what? Okay, so we're getting negative p. We're going to add 1. So it's going to be 1 over 1 minus p x to the p minus 1, 1 to b. It's going to be the limit as b goes to infinity. Maybe let's take the 1 minus p out just so we don't have to worry about it. 1 over 1 minus p times the limit as b goes to infinity. I guess I can't take the limit out until I know it exists. Yeah, whatever. Who cares? 1 over b to the p. I did cheat a little bit here, right? Obviously, I can't take the limit out, the 1 over 1 minus p out until I know the limit exists. But whatever. So here, what we're going to see is I need this here. Let me make this power clear. This is p minus 1, right? So this thing in the square brackets here will exist so long as p minus 1 is positive, right? Like this thing has to look like 1 over b to some positive power. So this will exist so long as that power is positive, which means this converges if and only if p minus 1 is greater than 0. Right? So what this does is this now says, this is true, if p is not equal to 1, then you converge if and only if p is strictly greater than 1. So it immediately throws out all the negative p's, all the p's less than 1. I guess the only thing left that we have to check is the case p equals 1. Obviously, this isn't going to work because we're going to get it log, and we know that it does not have a horizontal asymptote. Right, so this is now just 1 over x, and if you'll let me kind of skip the actual computation, so we're going to get log of b, and that does not exist. Right, and so we're done. The only values of p, which will guarantee to give you some sort of convergence here, occur when p is strictly greater than 1, and we're done. Right, so it's a computational proof. It's not even really a proof. You just like grind out the computations. Okay, are there any questions about that? Okay, this is now bugging me. I need to put the 1 minus p back in. Obviously, I can't take it out. Negative b. In where? Where do we want to take negative b? Oh, sure. I mean, right now the theorem is stated only that I'm going from 1 to positive infinity, like I'm not doing negative infinity to something. The theorem is still true, right? The theorem is true as well if you do, and again, you probably don't want to include 0, right? So you have to be careful about that. So you do something like negative infinity to negative 1 over x to the p dx converges if and only if p is greater than 1 as well, right? So if you want to prove that, you can. For us, it's, again, the proof is pretty much identical, right? The only difference that's going to happen is potentially that a sign change comes in, but like it's not, the proof is identical. So I would say in that case, yeah, we're not going to worry about b going to negative infinity. Now, you can't do b going to negative infinity in the proof that we did, because if we do the integral from negative infinity to 1, the function's not bounded, right? Because 0 is generally going to be a vertical asymptote of the function 1 over x to the power of p. So we have to be kind of careful about that, right? But yeah, if you want to restate it and reprove it, you totally could. No problem. Okay, and really what the p-test is if you think about the p-test, it's some sort of characterization of going to 0 fast enough, right? So what I want to say here, I guess last Thursday we were talking about, okay, morally speaking, for the improper integral to converge, the function has to kind of be getting smaller, right? Because you're adding a bunch of stuff infinitely often. So the function has to go to 0, but it has to go to 0 fast enough that you don't get this infinite accumulation of area, right? I've effectively already done the if and only if. Like, Kevin, you're right. Most of the time we would have to kind of like prove the opposite direction. The if and only if, though, comes in the case, right? This thing right, is I can basically, in this case, right? So again, in the case where p is not equal to 1, this limit converges if and only if p minus 1 is greater than 0, right? Because if, like, up until here, I have made no assumptions about p, right? So I'm computing, I get to this limit, and I say, okay, if p is greater than 1, this converges. And for this to converge, p must be greater than 1. So I get the if and only if just sort of immediately from here without having to assume each case separately, right? So I haven't made any assumptions up until this point other than the case that p was not equal to 1, so I could actually compute the integral. But that's how I get the if and only if. Yeah. Okay. So hopefully that takes care of it. And again, right, like what does this say? Let me just maybe write one of these down explicitly. So the integral from 1 to infinity, 1 over x squared dx converges, but the integral from 1 to infinity of 1 over the square root of x diverges, right? So even 1 over root x is going to 0, right? If this thing has a horizontal asymptote in the limit as x goes to infinity. 1 over the square root of x goes to 0, right? But it doesn't go to 0 fast enough. It goes to 0 so slowly that it actually does snowball, and it does begin to pick up an infinite amount of area. It goes to 0 really slowly, but it does pick it up. And 1 over x is somehow like this, this boundary case, in the sense that if you converge to 0 faster than 1 over x, you converge. If you converge to 0 slower than 1 over x, then you diverge. And that's only going to be true for things that look like 1 over x to the power of p. Okay, it doesn't turn out to actually be a true boundary. There are things that go to 0 faster than 1 over x that also don't converge. But right, like for 1 over x, for things that look like 1 over x to the p, that's your boundary condition. And here, of course, I've used like rational numbers. P actually here can be any real number, right? So if I look at this expression, I can do something like the integral of 1 to infinity, 1 over x to the, what do I want? 1.0001, right? Or any like real number that converges, right? But that thing diverges, right? So you can actually use any real number there if you want, like pi minus 17/4 or something. All right. So it's a little bit hard to see because here's the thing. If you graph 1 over x squared, right? What is 1 over x squared? It looks like this, right? Yeah, maybe let me draw that a little different. So here's y equals 1 over x squared. Okay, now if you graph y equals root x, 1 over root x, right? It looks something, it's going to look very similar, but it just grows it goes to 0 a little bit slower, right? Like this. And so again, we want that as we go to infinity, right? We're computing the area under the graph. And as we go off to infinity, we need that we're adding so little area. Such less area, fewer area. I'm adding less and less area to the point where it's not making a significant difference to the asymptotic value of the area. But with the square root of x, you are actually adding enough area, right? Even though, right, when x is equal to a billion, 1 over root x is a really small number, you're adding enough area that the area is actually getting bigger, right? It's not asymptotically approaching something, it's actually going off to infinity. And that's kind of what I mean by snowballing. Like as the integral is going further and further down the line, it's picking up enough area that this snowball is actually getting bigger and bigger and bigger. And it's actually going to go off to infinity. The snowball is going to get infinitely large. For y equals 1 over x squared, the snowball is picking up snow, but it's actually not changing in size, right? Like it's the amount of snow it's picking up is so small that it doesn't make a difference, right? And so that's kind of how I was thinking about snowballing, right? Is the snowball getting bigger or not? And with 1 over root x, it is. It's getting big really slowly, but it is picking up snow, or at least enough snow to make a difference. Is that okay? Okay. All right, so the first theorem that we're going to do here is called the basic comparison test. Now, when we start talking about sequences and series, these tests are going to come back in. So it doesn't hurt to get comfortable with them now. Okay, so the basic comparison test. And basically, what this says is if you know that there's an improper integral which converges, and there's another improper integral whose area you know is going to be bounded by above, it's basically going to force that to converge as well, right? So suppose f and g map A infinity to R. Do I need to assume they're integrable? No, I don't. No, I should. Yeah. Are integrable. Okay. So here's our setup. We've got these two functions. Both are integrable. We don't know if their integrals converge or not. And you know that g is always bigger than f. And they're both non-negative. So if the improper integral for g converges, then the improper integral for f must also converge. Okay. And you can see like this feels like lemma number 1, right? Lemma number 1 stated, you know that f is always bigger than g. If f diverges, it forced g to, No, G was always bigger than F. F diverges, forces G to diverge. This is the same sort of thing, almost like in a contrapositive form, right? And we're basically actually going to use exactly that. So prove, I guess I actually technically only need the monotone convergence theorem here, but whatever. So let's define F and G as the usual like so. Okay. Okay, so by monotonicity of the integral, we know that capital F is always less than or equal to capital G, right? So by monoticity, F of X is always less than or equal to G of X, right? That's because little f is always less than or equal to little g. Maybe let me put that in. Okay. And by the fundamental theorem of calculus, both of these functions are, non-decreasing, but we really only need that f is non-decreasing. I guess we don't even really need the fundamental theorem of calculus for that. It's just always true. If you're integrating a non-negative function, your integral is non-decreasing, right? So since f of x is greater than or equal to 0, f is non-decreasing. Thus, we have f of x is less than or equal to g of x is less than or equal to the limit as x goes to infinity, g of x, which is the integral from a to infinity of g, right? That's an upper bound. So f is bounded from above. Hence, this limit exists, right? That was lemma number 2. Lemma number 2 says if you know that your function is non-decreasing, right, and bounded from above, then this limit exists. So we have both of those things are true, and we're done. Okay, any questions about that? Maybe let me put the whole thing in view here. I guess I do actually need the G is non-decreasing to do this less than or equal to, but it's obviously true, right? Everyone's happy? I'm gonna assume yes. Okay, cool. Overjoyed. Detect a bit of sarcasm. Maybe not, though. Who knows? Okay, sure. Okay, so an important note here as well. So this is not actually how the basic comparison theorem is normally, or basic comparison test is normally stated, but we should state that the contrapositive is an important thing to remember here, right? So the contrapositive states that, so same conditions though, right? F and G are both non-negative functions, and F is always less than or equal to G. So the contrapositive states that if this diverges, then the integral over G diverges as well, right? So just keep that in mind. Okay. All right, so again, maybe let me zoom out so you can see the theorem statement, right? So the theorem statement is if G converges, F converges. Contrapositive is if F does not converge, then G does not converge. And does not converge, of course, is the same as diverges, right? So if F diverges, then G diverges. And so that's important, right? Because same sort of thing, basic comparison test isn't just a test that you can use to prove that something converges. You can use it to prove that things diverge as well. If you can show that G is a function, and it's always bigger than a function which diverges, then G must diverge as well, okay? So if you want to show convergent, show that you're bounded above by a function which converges. If you want to show divergent, you show that you're bounded below by a function that diverges, right? Does everyone see that? Convergent, bound above by a convergent function, divergent, bound below by a divergent function. So you can use it for both. And I think most statements of the basic comparison test kind of state both, but of course we know what contrapositives are. So we can kind of like, make our lives a little bit easier just by stating it like this. Yeah, exactly. So hypotheses still have to be true. Namely, this is kind of the crux condition right here, right? So both still have to be non-negative because we need that they're increasing, right? Like otherwise, if one of the functions sort of oscillates back and forth, precisely like sine, right? We can bound sine from, what do I want? We can bound it above by a converging function, but sine itself doesn't actually converge because it is allowed to oscillate back and forth. So we definitely still need this condition to be true. All right, let's do some examples. So let's say determine, and remember what I mean determine that, actually, no, sorry. Let's say determine if it converges. So if, what do I want to do here? X. Okay. So let's determine if this thing converges. This is actually really hard to integrate, right? Which means that we'd be fairly hard pressed to actually get a value for this. But let's not worry about that. Let's just determine if this thing even converges in the first place. And what we effectively want to say here is, well, e to the x goes to 0 really, really quickly, right? To the point where we hope that that e to the x term isn't really affecting the integral. So we're going to do a little bit of manipulation. Basically, I want to say this thing looks like 1 over x squared, right? I've got an x in the numerator, I've got an x cubed in the denominator, and then the e to the x term is making the denominator go to 0 really, really quickly. So morally speaking, I want to say this thing looks like 1 over x squared. So let's do it. So note that x over x cubed, and implicit in this conversation, right? You've been given the domain on which this is true. So in this case, it's 1 to infinity. And so you can use that if you need to. So here we're not going to need it. But another thing to keep in mind, and hopefully you all believe this, if I'm trying to show the integral from 1 to infinity converges, and the best I can do is show that the integral from 70 to infinity converges. Well, if the integral from 70 to infinity converges, then 1 to infinity converges as well, because the only difference between them is that you added the integral from 1 to 70, which you knew is finite anyway, right? So you have to keep it, pay some attention to that domain. But if you can just show that at some point it converges down the line, then you get convergence for the whole thing. Okay, so we get that this is true, right? Just via, x over x cubed plus e to the x less than or equal to 1 over x squared, just by some fairly simple manipulation. 1 over x squared converges by the p-test. Right, so by the BCT for basic comparison test, this converges as well. Converges by B, B, C, T. Okay? And we're done. So that's pretty easy. Now, of course, we can have more complicated examples. So maybe let me do that one next. And again, don't hesitate to ask any questions if something didn't make sense. So example, let's say determine if, all right, I'm going to write something a little bit nasty down. If 1 to infinity, 1 plus 4 sine to the 6, 3x over root x dx converges. Okay, and this isn't too bad, right? There's a lot of like red herrings here. There's a lot of things which is designed to make this look worse than it is. So basically we know sine to the 6 is always between 0 and 1. Right? If that was an odd power, it'd be a different story. We'd be in a little bit more trouble. I'll show you how to deal with that in a little bit. But because we were lucky enough here that we got lucky, right? Because, you know, I designed the question, lucky enough here that we had an even power, we're able to do this sort of manipulation, which very quickly means we can replace the, well, here, let me kind of tell you what I'm thinking here. So I see, you know, the sine thing, the sine is just oscillating back and forth. It's not, morally speaking, it's not contributing significantly as x goes to infinity, right? It's just kind of oscillating between 0 and 1. Which means the important thing here is 1 over root x. Now we know that 1 over root x diverges. So my suspicion is that this diverges as well. So what I want to do then, to use the basic comparison test, is I want to try and bound this thing below by 1 over root x. So that tells me I'm probably going to use this end of the inequality, right? I'm not going to use this end. Okay, I would use that end if I were trying to show, right? So I'm going to use this end if I'm trying to show divergence. And I would use this end if I'm trying to show convergence. Do you all see that? Right? Because with convergence, you're trying to show you're bounded above by a convergent function. With divergence, you're trying to show you're bounded below by a divergent function. So here I'm going to use the that first inequality in order to get what I want. And if you try the other one, you see why it doesn't work, right? So we're going to get 1 plus 4 sine to the 6, 3x over root x is then going to be greater than or equal to, I can just replace the sine to the 6 with the 0, 1 over root x, which diverges by the p-test. So this diverges as well. Okay. And keep in mind, you have to be careful about the inequality that you use. If we had used the other one, maybe this is worth pointing out right now. If we'd used the other inequality, so if we had used the other inequality, what would we have gotten? We've gotten 1 plus 4 sine to the 6, 3x over root x is less than or equal to 5 over root x, right? But this is useless for the basic comparison test because the thing on the right diverges. And if you're less than something which diverges, that doesn't tell you anything. That's like saying my number is less than infinity, less than or equal to infinity. What does that tell you? It could be anything, including infinity. It could be a finite number, could be infinity. This is not useful for us, right? Right? So you have to bound above by something converging or bound below by something which is diverging. And of course, you can't do both simultaneously. That's not possible. But one of your inequalities generally could be useless and the other one could be useful. So you have to, kind of think ahead of time. I mean, you could just try both and see what happens and say, oh, well, this one's useless, and so I'm going to go with the other one. But if you look at it, often you can kind of look at your integral and have an idea of like, oh yeah, okay, sure. That seems like that'll probably behave like this thing. And that thing converges or diverges, right? So that's what we're trying to figure out. Okay, so are there any questions about that? No, we're good. All right, let me maybe give you a third example to show you that like the basic comparison test though, as nicely as this all worked out for these two examples, a big part of that is of course because I doctored these examples so that they would work out nicely. But you can come across very quickly examples which don't work, or at least examples which are hard. So this example is not impossible, but it's much tougher. So, okay, what about this thing? What do I want to start? I don't want to start at 1. Let's maybe start at 3. Okay, so what if I said, figure this one out? And this one actually can be done explicitly. Like this integral is not hard to compute. It takes a little bit of work, but it can be done. So I said, what about this one? Again, I want to say this thing looks like it's a 1 over x squared, right? And 1 over x squared converges. So this is probably, because the -4 isn't contributing. When x is 1,000, x cubed is what, a billion? And so, a billion minus 4 isn't that much different than a billion. So this thing is behaving like it's 1 over x squared. The problem is that, of course, if we try to do BCT, so if we try to manipulate this, let's say in the obvious way, if we try the obvious manipulation, all right, what do we get? So we get x over x cubed minus 4. Uh-oh, because that minus sign is there, I get this. That's useless. Right? Because I'm saying, right, so we need to compare, right? Which means we need a different theorem. And maybe Adam, that you're like, what the next theorem is. But basically, right, we're saying this thing is bigger than something which converges, but that's like saying this thing is bigger than or equal to, say, 7. But infinity is bigger than or equal to 7. Like that doesn't give us any, any valuable information. F of 3 and g of 3, where g is equal to 1 over x squared.
It's too hard to write. Like my idea was like, if we compare like x divided by x cubed minus 4 to 1 over x squared, like we compare, for example, their derivatives, and then we compare them at 3, we can prove that like one is bigger than the other for every number, because like comparing the growth maybe.
Okay, so this is interesting. I mean, the problem here is that I've just, so one of them is always bigger than the other, right? But it's 1 over x squared, which is always bigger than x over x cubed minus 4. Right, here's your g of x, right?
And because it's always bigger, then we can write f of x is smaller than g of x. So the integral of g of x is bigger than the integral of f of x. And then like we make 1 over x squared. We use the pi test to see that 1 over x squared converges. Thus, the other one converges too.
Right, which is sort of the right idea, except of course we don't know that, like we know for sure the g of x is not bigger than f of x, right? Like I've just proven it, right? Like in this thing here, right? This is true. This is true for all x, which are, it's actually just true for all x. So we need g of x equals 1 over x squared is a good idea. And basically the theorem I'm about to do is morally what your idea is, which is like they basically are the same function. They grow at the same rate. The growth is sort of the important thing here, right? So they're basically the same, but in practice, I can't use exactly 1 over x squared. So if I wanted to do a basic comparison theorem sort of thing here, I would need to do something different. Which is to do something like, show that the thing on the left is always less than or equal to, 1 over x squared plus 20 or something like that, right? Like find some sort of number that I could throw in there to make this true. And yeah, there is one that we can do actually. It just gets a little bit nasty. So what I would probably do actually is I would do this. I shouldn't have used x cubed minus 4. I didn't have any plans on actually doing this example, but if I were to do this, I'd probably do the following. I would do 1 over x cubed minus 4 is equal to x divided by x minus the cubed root of 4 times x squared minus 4 to the 1/3 x minus 4 to the 2/3. Maybe let me write it like this. Right? And since we're bigger than 3, I actually probably want, so let's assume that we're bigger than 4, so that this thing now is less than or equal to, but here's where I run into an issue, right? So, because I'm going to keep the x upstairs and I don't want that. This isn't going to end up working. So let's not do that way. Anyway, the point is you have to get some sort of manipulation, right? Like hopefully, I don't know if this is true, but maybe this is true. And of course we'd have to prove this, right? If this is true, we'd have to prove this. But once I've got this, then hopefully I can do something with the right-hand side, right? And the right-hand side actually is arctan. So, we can prove that converges without too much trouble. But that's the sort of thing that you would need to do, right? 1 over x squared isn't going to work by itself, but if you throw in a couple of things there, you can make it work. But your algebraic, your inequality manipulations now are much nastier, right? Because we have to prove that this is true. And inequalities are really hard to prove as a general idea. Equalities are easy, right? Because they're so rigid. There's only so many things you can do. Inequalities are much more flexible, and that typically makes them much more difficult. Now, the point of me introducing this is more to say, we need something better than the basic comparison theorem test, right? Like what we want instead is I want to be able to look at this function right here and say, it shouldn't matter if that's a -4 or a +4. 4 is not a big deal, right? When x is really, really big, because if this was x cubed plus 4, the inequality would work out, right? So how is it that a difference of 8, the difference between being x cubed minus 4 and x cubed plus 4 is the thing that's stopping me or is making my life really, really hard, right? In one case, it's an easy inequality. In the other case, it's a hard inequality. That's absurd. That literally the number 8 is what's screwing me up as x goes to infinity, right? That's ridiculous. So what we'd like to say is, can we figure out some way of saying, listen, this thing just is 1 over x squared, right? Up to some small degree of error, this is 1 over x squared. And the answer is yes, we can do that. So I'm going to write the theorem down, and then we'll take our break. But it'd be nice if I can write the theorem down. That way you can stare at it and you can be like, oh, okay, that seems reasonable. So theorem. So this is the limit comparison test. And you can call it the LCT. We'll all know what that means. So suppose, same sort of setup, right? Infinity to R are integrable and f and g are both non-negative. Okay, we don't need any condition. Here's automatically where we're winning. We don't have any sort of inequality relationship between f and g. We just need that they're both negative for now. Okay, now if, let me just make sure I didn't miss anything. Right, if exists and is non-zero, converges if and only if. Okay, so this thing right here, this condition says f and g do the same thing as x goes to infinity, right? If this limit exists, let's say this limit is equal to 7, then what we're basically saying is that as x goes to infinity, g is 7, or f is 7 times g of x, right? They're basically the same function up to some sort of multiplicative constant, and that constant is whatever the value of the limit is. They effectively behave the same way. And if they behave the same way, if they do exactly the same thing as x goes to infinity up to multiplying them by some number, then one of these functions will converge if and only if the other function converges, i.e., if f converges, g converges. If f diverges, g diverges, right? They have to do the same thing, right? So this theorem says, if f and g do the same thing as x goes to infinity, then their improper integrals have to do the same thing as well. Does that make sense? And we see like this is great because we don't need to worry now about doing this sort of manipulation of inequalities. Doing this limit, believe it or not, is most of the time actually easier to do than manipulating inequalities. Okay, so I'm going to leave you with this theorem. We're going to I want you to think about this for a little bit. Even better is if you want to try and prove it. That would be cool. Oops, I deleted the limit. But if you want to try and prove it, great. The proof actually isn't that hard. But this theorem says if the functions behave the same way as x goes off to infinity, their improper integrals behave the same way as well. Okay, so let's break. By my watch, it's about 10:08, or it will be by the time I'm done speaking here. So we'll come back by 10:18 by my watch. We'll take a nice little 10-minute break. I'm going to prove this for you. We'll do an example of how we can do it, like how we could use this theorem in order to give us a hand. And then I will point out that, oh, unfortunately, both of these theorems have this restriction. How do we deal with that? Because we'd like to be able to prove that things converge when they're not just non-negative, right? So how do we fix that part? And so we'll introduce another theorem for that. Okay, so 10 minutes, and I will see you all here back then. I'll see you all back here then. There we go. Those are the words. Okay, we're back. And now we're going to prove this thing. The proof is, again, surprisingly not too tricky. It really, again, just kind of comes down to, oh, what is the definition of a limit? And then basic comparison test, and, we win. Like, that's the end of it. Okay, so let me just get going. All right. So the proof runs as follows. Proof. Okay, so we know the limit exists, and in particular is non-zero. One of the great things that you can always do in this case is you can set epsilon to be some form of the limit itself. Now, I think in the book, I actually use 1. I set epsilon to be 1, but I want to do something a little bit different today just because it makes the proof actually a little bit easier. So I'm going to take epsilon, or I guess I should say, first let L be the limit. Right, which I said we know is not 0. And in particular, it has to be positive as well. Right? And again, if that doesn't make sense, just like, let's think about this for a second. F and G are both greater than or equal to 0, right? So their limit also has to be, right? There's no way that their limit could be negative. And we already said that it can't be 0. So the limit itself, if it exists, must be strictly positive. Okay, so now let's let epsilon be equal to L over 2, which we can do because we know that that number is positive. And then let's, find, let's go far enough into the positive real numbers to guarantee that our two functions, f and g, always live within that little epsilon band. Okay, so we're going to set epsilon to be L over 2 and choose n in R such that f of x minus g of x minus L is less than L over 2 if x is greater than or equal to n. Right now, it's been a long time since we talked about limits going to infinity, right? But hopefully you remember the epsilon delta, quote unquote, definition of that limit is, for every epsilon, there exists an n such that if x is bigger than or equal to n, f of x minus L is less than epsilon, right? So we don't have a delta. Instead, we have, if you're far enough into the positive real numbers, you can guarantee that your function is always close to your limiting point. So what I'm going to do now is I'm going to take this epsilon delta definition and I'm just going to expand it a bit. And you're going to see why I use the L over 2. And again, you can use something else if you want. L over 2 just makes your life a little bit easier. Okay. So I'm going to take the f of x divided by g of x minus L. So I'm going to say equivalently, we're going to have, maybe let me break this into two pieces. Actually, just do the math, because I think it's probably pretty easy to get confused at this part. Oh, sorry, that should be just strictly less than. Right, and then if I add L to both sides. Less than 3L over 2, like so. Okay, and now G is non-negative, so I can just multiply both sides by G, and then if I do that, the inequalities don't change. Right, so I'm going to get L over 2 G of x is less than f of x is less than 3L over 2 G of x. Okay, and now we're basically done. So at this point, I haven't done anything, right? All I've done is kind of set up these sorts of bounding relationships. Now, what are we trying to prove, right? So if we look at that bottom line in yellow, we want to show that the improper integral of f converges if and only if the improper integral of g converges. So let's assume to start that the improper integral of g converges, right? So I guess it's maybe a little bit weird. We're going to start in this direction, but you'll see why in a second. I think it's the easier direction. So suppose the integral of g converges, right? Well, if this converges, so too does 3L over 2g. Right? Like, I guess I didn't explicitly state that the improper integral was itself linear, but it just sort of immediately follows by the limit laws, right? Like if you were to take a limit as the top, what do I want? What's the word I'm looking for? The top thing of integration, right? It goes off to infinity. Well, it's just your normal finite limit. So you can pull the 3L over 2 out and this whole thing converges, right? So this converges as well. Is everyone okay with that? Does that make sense? Like if G converges, so too does 3L over 2G, like, right? That's just a constant, right? I didn't do anything kind of crazy there. Everyone's okay with that? Again, yell out if you're not. Therefore, if we now use this, right? By the basic comparison test, we're done because I bounded f above by something which converges. So since (3L/2 g of x) by the BCT, the integral of f converges, right? So what have we done? We've proved that if g converges, or the integral of g converges, the integral of f converges. In the other direction, we're going to use the other inequality, right? So suppose that f converges so that the integral from a to infinity of, what do I want here? 2 over L f converges as well. Right, so now if I use this inequality, the other one, right, the one on the left there, that I've underlined in yellow, so what do I want to say? So now since g of x is less than 2 over L f of x by the BCT, g converges. Right, and we're done. So it all, at the end of the day, it all comes down to this inequality, right? Up to, some constants. Oh, sorry. You know what? I guess maybe I shouldn't say the integral from a. I guess I should say the integral to n converges. This converges, so the integral. Here, let me actually maybe write those in red so you can see what changes I'm making. Okay, so the best I can do is guarantee that those converge if I put an n there, right? Because that's where this inequality is true, is x has to be bigger than n. But in both of those cases, if you know that the integral converges from n to infinity, then it converges from a to infinity as well. Right, so maybe let me just, I know most of you probably can't do this if you're writing in pen and paper, but the integral from a to infinity of f is a to n plus n to infinity, which both exist. As required. Does that make sense? So really, I only proved convergence from n to infinity, but it doesn't matter because if you're trying to prove the integral from 1 to infinity exists and you prove the integral from 3 to infinity exists, well, that does it, right? Because then the only difference between those two things is the integral from 1 to 3, and you know that exists because you assume that your function was integrable on every interval. And then same sort of story, right? But a to infinity g is equal to a to n g plus n to infinity g, which both exist as required. Does that make sense? Is everyone okay with that? It's just some sort of technical thing. I wanted to include it in there because I kind of alluded to this earlier. I guess I probably could have just skipped to the answer and said a to infinity of f exists or whatever. But I think it's worth kind of pointing this out, right? If you're in the improper integral, you don't care about what happens early in the integral. You only care about what happens at the end of the integral, right? As you go off to infinity. So if you can prove it as you go off to infinity for any finite fixed point and for your lower bound of integration, that does it for the whole thing, right? So the fact that we can only do it for n to infinity, not a big deal, right? Really doesn't affect us. So I want to make sure there's no confusion there, right? Is everyone okay? Okay, if nobody says anything, I will assume it is okay. Okay, cool. And yeah, like I said, we're going to see the exact same thing in sequences too, right? You're going to try and show the sequence, or even like let's say we prove the same thing for functions, right? Like if you want to show that the function has a limit as you go off to infinity, you don't care about what happened at the beginning, right? You only care about what happens at the end. Is it true a sequence converges if and only if all of its subsequence converges from the basic comparison theorem or basic comparison test? The theorem is true, but not because of BCT, right? It is true that if a sequence converges if and only if all subsequences converge, but that's not related to the BCT. That's just a property of sequences. And so we'll see that when we get there, but basically subsequences converge faster. And then the original sequence is a subsequence of itself. And so that's the if and only if direction. But yeah, it's not BCT. When we get to convergence and when we talk about comparison tests with sequences, we'll actually be talking about series, right? Like if the analog of a function is a sequence, then the analog of the integral is a series where you add up all the elements of the sequence, right? And for those of you who don't know what that is, don't worry, we'll get to that. I don't expect you to know what that is going in. Yeah. Okay, so as an example, I mean, first of all, why don't we do the example we were just talking about, right? So determine if, what did I say? 3, I think. X cubed minus 4 converges. And again, I was kind of saying morally this function is just 1 over x squared, right? So that is our comparison function. That's what we're going to try and compare it to. So solution, let's say let f of x be the thing that we're trying to integrate. And this is often the trickiest part of this sort of procedure is trying to figure out what to compare it to. In some cases like this, it's fairly obvious, but in other cases, what you often want to do is say, what are the things that are dominating in the limit as you go to infinity, right? Like, which are the things that are going to be the biggest, right? The things which are most restrictive to you converging to 0. And so certainly the 4 is not a contributing factor, right? Okay, so this is our function f and g. Now, remember, in order to be able to apply the theorem in the first place, we have to, quote unquote, show that these things behave the same as we go to infinity. Namely, we have to take their quotient and take a limit of that quotient. So taking a limit, we're going to get the limit as x goes to infinity, f over g. So that's going to give me this thing, right? Here I'm using the fact that since g is 1 over x squared, 1 over g is just x squared. And something very nice here happens. We get x cubed over x cubed minus 4. And I don't remember, did I show you guys how to do these limits? Like this is the sort of thing that they would spend a lot of time doing in 135, 136. But did I show you how to do this one where you divide top and bottom by 1 over x cubed? I bet a bunch of you probably saw this in high school anyway, right? Maybe I'll do it this time. What is LP? Are you thinking like L'Hopital or? All right, so what you do is, okay, sure, yeah, you could do L'Hopital if you wanted to. Kind of the traditional approach here is to divide, where you have just a rational function, divide by the biggest power. So I'm going to divide everything by x cubed. And then you say, oh, look, the 4 over x cubed term goes to 0. So the only thing that survives is a 1. As a dirty cheat, if you have a rational polynomial, so you have a polynomial in the numerator, polynomial in the denominator, you'll have a finite limit precisely when the power of the numerator is the same as the power of the denominator. And in that case, the limit is actually the ratio of the coefficients of the highest powers, right? So in this case, got an x cubed in the numerator, its coefficient is 1, x cubed in the denominator, coefficient is 1, so the answer is 1 over 1, right? Either way, we get this finite limit here, so therefore we can apply the basic or the limit comparison test. So f converges if and only if g converges. We know g converges by the p-test, therefore f converges, right? So thus, the LCT applies. And, 1 over x squared, or I guess 3 over x squared, converges by the p-test. So this converges. Right? LCT is about comparing growth of the function inside the integral that are like the derivative of the integral. Thus, this is a link between the limit of function and its derivative. Let me think. I mean, ultimately, yes. Again, sort of in the sense that like they are close, and in particular because in the limit comparison theorem statement, oh man, how far do I have to go? Okay, this thing up here, the statement about the limit existing, is also sort of a condition on the derivative, right? In fact, we know by L'Hopital, both f and g are going to 0, or should, morally speaking, again, go to 0. If they both go to 0, then this is a L'Hopital, indeterminate form, 0 over 0. You can apply L'Hopital, and this limit will actually be equal to the limits of the derivatives, right? In that case, if you're lucky. So there is a sense in which this is a relationship between the functions and their derivatives. But on the other hand, this, morally speaking, has to be true anyway. If the functions f and g are asymptotically behaving in the same way, then their derivatives also need to be asymptotically behaving the same way, right? Like if one of the functions is growing much faster than the other, then there's just no way these two functions will have a finite limit, right? They just can't coexist together, or they won't give you a finite limit because, yeah, f is getting really, really big, or maybe g is getting really, really big, right? Of course, g can get really, really big and give you a limit equal to 0, but that's not, strictly speaking, within the purview of the limit comparison theorem, or limit comparison test, right? So, this is one of these things you kind of have to make this call as to whether or not you're going to use the basic comparison test or the limit comparison test. And, if you can use the basic comparison test, it's often much faster because you don't have to do this limit computation that I had to do here. That being said, basic comparison test is often very restrictive, right? Like if the inequalities don't work out, it could become a little bit tricky to make them work out. And then you have to go to limit comparison. If you do enough of this practice, you can just kind of stare at them enough and you'd be like, oh, okay, I can guess which one I need to do. It's very tempting to just default to the limit comparison test because it pretty much always works. It's very rare that the limit comparison test doesn't actually work, right? A couple of points maybe to make here as well. You might say, well, what if I switched f and g, right? Like what if I let f be the function 1 over x squared? And what if I let g be x over x cubed minus 4? And the answer is that doesn't make a difference, right? Because when you compute the limit, right? When I compute this limit, if I had switched them and I had, basically that would be the same as doing the limit is g of x over f of x. And since this limit here is not 0, it's a finite number, it's not 0. If you take the reciprocal, the limit laws just say you would take the reciprocal of that as well, right? So in this case, it's 1, so it's kind of boring. But if I had done this computation and I had gotten a limit of 2, then flipping f and g would have given me a limit of a half, right? If the limit had been 10, flipping the role of f and g would have given me a 10th. So it doesn't matter because all you need is that the answer exists and is positive, right? It's a positive finite number. And so switching the role of them just takes the reciprocal, and that's still a finite positive number. So the limit comparison test will work regardless of which function you take to be f or g. You're very much kind of safe that way. You might also, people might be upset because I said this converges by the p-test, right? but I used 3 in the lower bound. Again, I want you to think about this for a bit and convince yourself, even though the p-test says 1 to infinity, it implies the existence of this, this integral from 3 to infinity. Because if 1 to infinity exists, certainly 3 to infinity exists, right? The only difference between 1 to infinity and 3 to infinity is the integral from 1 to 3. And that's finite. That's not going to make a difference in convergence, right? Any questions? Everyone's okay, hopefully. But if not, let me know. Otherwise, I'm going to do the hardest of the 3 tests that we're going to do. But again, super useful because, again, all of these things that we're doing will have analogous theorems when we get to sequences. So there's a basic comparison test for sequences and series, really for series. There's a limit comparison test for series. And what we're about to do also has an analog for series, which is typically, again, one of the things that students really struggle with. The thing that I want to now fix, in both of these tests, our functions had to be non-negative, right? We needed functions which were greater than or equal to 0. Really, for this function, we even need that our function is mostly strictly positive because I'm taking a quotient, right? So we need our functions basically to be positive, non-negative at best. But of course, I could ask you to compute convergence for functions which don't do that. So this is actually a really restrictive requirement. How do we deal with this? This isn't a perfect solution, okay, but it is going to fix a lot of things. So the first thing we have to do is talk about a definition. This is a very weird definition. Okay, so if f mapping a to infinity to r is integrable, we say that, here's the weird thing. Is absolutely convergent. Okay, this is weird. This is really weird. So we need to think about this for a second. We've got this thing, which is the improper integral. And we said if this, this thing converges if it exists, if it's a finite number. So now we're going to say that this improper integral is absolutely convergent. So we're going to describe this improper integral using a different improper integral, right? That's kind of weird. So right now, I can say that this improper integral is absolutely convergent without knowing if it converges or diverges, right? This integral is absolutely convergent precisely when the integral of its absolute value converges. That's weird, right? Because right now we don't know anything about whether or not the improper integral itself converges or diverges. That's a little bit weird, okay? And we were going to say it's conditionally convergent. Or converges conditionally. Suddenly I can't think about how to spell conditionally. Hopefully I spelled it right. Is conditionally convergent if this converges but the absolute value diverges. Okay, so this definition of conditional convergence seems to be hinting at something. And this is something is what I'm going to prove in a second here. But it seems to be hinting at something. And what it's hinting at is that if an improper integral is absolutely convergent, it seems like it might be convergent as well, right? So That's kind of a reasonable hypothesis or conjecture to have, that if you're absolutely convergent, then you're actually convergent. And in fact, if you think about this even more deeply, it perhaps becomes more obvious. When I take the absolute value of the function, right? When I do this thing right here, when I take its absolute value, chances are it's less likely to converge, right? The absolute value of the function is less likely to converge because I don't get any nice cancellation happening, right? If I'm dealing with the original function, it could go above the x-axis and then beneath the x-axis, and I could get some nice cancellation of things, right? That ultimately results in something being convergent. But when I take the absolute value, there's no cancellation that can happen, right? All the area is positive. You know, the absolute value pushes everything above the x-axis. And it seems like I'm more likely to get this snowballing effect where I actually result in something which is not convergent. So from that perspective, it seems reasonable to suspect that if you're absolutely convergent, then you are convergent. This turns out to be true, okay? It's a little bit tricky to prove, but it does end up being true. So theorem, how do I want to say it? Yeah, if it converges, absolutely, then it converges. And this is going to fix, at least sort of be a reasonable fix to our problem, right? So the basic and limit comparison tests required that our function be non-negative. If we take so if I give you a non-negative function, what you could do is you could take its absolute value, prove that the absolute value converges, and then this theorem will tell you that the original function converged, right? So this gives you your strategy. I give you a function, it's not non-negative, take its absolute value so that it is non-negative, apply the basic and limit comparison tests, prove it converges, and you win. This only works for convergence though. It does not work for divergence. Okay, so let me try and prove this for us first. Okay, so what we're gonna do, this proof is a little bit weird, and I don't think it's super intuitive because you just have to play with some inequalities. So what I'm gonna do is I'm gonna define a new function like follows. So define g to be the function f plus the absolute value of f. Okay? So this is a little bit weird, but bear with me here. So that, what I want here, 0 is less than or equal to g, which is less than or equal to 2 times the absolute value of f. Okay, stare at that inequality. Convince yourself that it's true. So, right, when f is already positive, then if f is already positive, g becomes 2f, right? So it stays very, very positive. Anywhere where f is negative, g is 0, right? Because if g is negative, if f is negative, then the absolute value of f is the same value but positive, and when you add them together, they cancel each other out, right? Does everyone agree? Yeah, exactly. Yeah, and then the other inequality is because f is less than or equal to its absolute value. So this is true. And the great thing about this now is, boom, basic comparison test. So we know g converges, right? Right? Because remember, we assumed that f converged absolutely. So we know that thing, when I take its improper integral, converges, right? Because yeah, if the absolute value of f converges, so does 2 times the absolute value of f, right? So by the basic comparison theorem, I have bounded G above by something which converges, so G must converge as well. Okay, now that's not what I wanted to prove though. I wanted to prove that F converges, right? Not G, F, but that's fine. Because I can write F as G minus the absolute value of F, right? And so how do I want to do this? Okay, I'm going to write down something, and if you don't believe it's true, yell at me. And I will prove this in more detail if you need. Why does 2 times the absolute value of F converge? Yeah, sure. So remember, we assumed that F converged absolutely, right? So that tells us that A to infinity absolute value of F converges, right? And if the improper integral of the absolute value of F converges, then so too does 2 times it. Yeah. Okay. Does everyone believe this, right? I'm using here the fact that both of these limits exist, but is anyone upset with this line? Does anyone want me to write it out? Like, as soon as I start writing it out, I think people will be like, oh yes, I see. But if anyone doesn't see, let me know. Everyone's okay? And it really is, yeah, it basically, so it's additivity of the integral and the limit laws though, right? So very specifically here, I guess, actually I'm kind of kicking myself for not maybe stating this. So maybe let me just kind of sign this off. But this is something you all should prove. So prove that the improper integral is actually linear. And the theorem that we want here is, or maybe this is just a proposition, right? Is that if integral A to infinity F and the integral A to infinity G exist, or so let's say converge, then this converges. Right? And we need this first part, right? This hypothesis has to be true. And because if you have this, the proof becomes very quick. Right? We have the limit as b goes to infinity of the integral from a to b, f plus g, right? Now we have additivity of the integral. A to b f plus a to b g, right? So this is additivity of the integral. Okay, but I still need to use another result. Which is this one, right? And this is the limit laws, like we know this one. A to b g, so this is the limit law. And for that one, I need that they both exist, right? And now the whole limit exists and is equal to what we want. So we're done. So I have to use two things there, right? I have to use both this additivity property of the integral and the additivity of the limit if both of the limits exist. So that's kind of where I'm using that. Of course, this also applies for scalar multiplication. I've kind of implicitly been using that the whole time, right? Like I even use it right here where I say, if you're absolutely convergent, then 2 times the absolute value of f also converges. But you can imagine the proof is the exact same, right? You use the fact that you can take the scalar out of the integral, and then you use the fact that, again, by the limit laws, you can take that scalar also out of the limit, and then you're done, right? Like you've proven everything that you want to prove. So it's both, because we're taking a limit, it's both limit laws and properties of the integrals, but as long as you have this, you're done, right? And everywhere I'm working here, I'm working with convergence. Okay, so the proof is pretty short, but it requires this little trick that you have, this weird G thing, and that you define G appropriately in order to make everything fall apart. Notice though, this theorem, again, okay, this theorem is great because it will help you prove that things converge, but it does not help you prove that things diverge, right? Nothing about this will give you a hint, because it turns out there are conditionally convergent functions. There are conditionally convergent improper integrals. So what that means is the improper integral itself converges, but it does not converge absolutely. And so this theorem doesn't tell you anything, because you would take its absolute value, you would get its absolute value diverges. Okay, that doesn't tell you anything about the original function, right? If you take the absolute value of a function and that function diverges, you've learned nothing, because this isn't an if and only if about absolute convergence and convergence, right? You don't know anything about the divergence properties. So I'm going to give you an example. I'm going to make you do the example of a conditionally convergent improper integral, but I'm going to make you guys do the example in your next homework, because it's a slick little example, and it takes actually a fair amount of work. So note, we can't use this result to prove divergence since there are conditionally convergent integrals. Okay, and the one I'm going to give you, I'm pretty sure is the integral from 1 to infinity sine x over x dx. Conditionally converges. Okay, it does not converge absolutely, it only converges conditionally. All right, let me very quickly though give an example of how we could use it. All right, so show that, which one am I going to do? 2 to infinity sine t squared over t to the 4 minus 2 dt converges. Right? Again, morally, I look at this thing, I say the sign isn't doing anything. It's oscillating between plus or minus 1, but it's really not contributing. As the, as t becomes very, very large, the denominator is the dominant factor, right? It's forcing this thing to become 0. The problem here is, of course, I can't apply basic or limit comparison tests, because the sign, while it's not really contributing as t goes to infinity, it is causing my function to oscillate between being positive and negative. And so I can't use BCT or LCT. What I can do, though, is take its absolute value. Right? So we'll show this is absolutely convergent. And hence convergent. Okay, so if I take its absolute value, okay, well, I can't really do anything directly, but what I can immediately say is this. I can basically get rid of the sign because when I take the absolute value of the sign, right, I always get something which is between 0 and 1. So it's very similar to what we had before when we were talking about that sign to the power of 6. And I said, because it's to the power of 6, I can say this is always between 0 and 1, and that's very advantageous. What do we do if we have an odd power? Well, with an odd power, we can do the same thing as long as we're willing to take the absolute value, okay? Moreover, we know that the integral is 2 to infinity, and on 2 to infinity, right, that's where I'm looking at for my improper integral. On that interval, this function is always, the denominator is always positive. So I can actually just get rid of the absolute value, right? Then what we would do is we would limit comparison theorem, right? So by the LCT. So let me be a little bit lazy just because we're running out of time. 2 to infinity, 1 over t to the 4 minus 2 dt converges. So by BCT, the absolute value converges as required. Okay, so obviously I skipped a step here where you actually show that this thing converges, but hopefully you all agree, like you do the evident thing, right? You compare this to 1 over t to the power of 4. That's definitely just going to give you a limit of 1. T to the 4 converges by p-test. Boom, you're done. So you can see this result uses everything, uses absolute convergence, basic comparison test, limit comparison test, and all three of those things combined allow you to solve this pretty easily. Okay, so that's going to take care of this. Are there any questions about this before we take off? Everyone's happy-ish? Okay, sweet. Very good, very good. I love it. All right, sweet. So that covers that. Thursday, we're going to talk about what happens when the function is unbounded. So the domain is bounded, but the function is unbounded. For the most part, though, I'm just going to be like, hey, look, all the theorems are the same. Just adapt things appropriately, and that's going to take care of that. All right. So yeah, I don't think I have anything else to say here. That'll finish this off for today. Thank you, everyone, and I'll see you on Thursday.